Hello everyone, welcome to a new tutorial on microscopy image browser. And in this episode I'd like to show you how you can train a deep learning network on your data and how you can use this trained network to predict new unannotated datasets. Today I'll tell you about the user interface, and as an example we will train network over 2D images. So the 3D datasets are also possible, but I will explain it in the following video. So the tool is available in Microscopy Image Browser version 2.7, and it requires deep learning toolbox of MATLAB and computer vision toolbox of MATLAB together to work. However, if you are using compiled version of MIB, both of those packages should be kind of installed automatically, so you don't have to worry about this. You can find the tool in the menu, Tools, Deep Learning Segmentation. Okay, so that's the window of DeepMIB. And before starting, so you should be sure to have a modern graphic card. So in my case I will use the GeForce GTX 1080 Ti, and if you don't have any, then in this case this workflow won't work for you. It's going to be too slow. The first thing that we need to start our project is to defining one of these available networks. So what you can see from this list, we have an option of 2D UNet or 3D UNet, or we can use the SegNet. The SegNet, it's more, as I understand, more kind of, it was used more for semantic segmentation of images collected like our normal lives, like on the streets, taken with normal cameras. But in biology, it seems that UNet configuration works better. So today we will use this 2D UNet. And for those who are not familiar with UNet, so you can go to this website, and there is a publication mentioned that describes the process. So in brief, we have this network which has this U shape, and because of that it's named UNet. And in the beginning we have our input image. It could be the full image or it could be a page from that image, and then this image is subjected to a number of convolutional steps. Like, for example, there are 64 individual filters applied to this image. And what happens behind the scene here, you can kind of find details in the various tutorials or explanation articles across the net. But in quite quickly, I'll show you this article. And what happens at that level here, the convolutional level, is that we use a filter. In this case, has 6 by 6 pixels, and it has a kind of encodes certain random shape, and the shape network is generating and tries to find the best suitable shape. So we're not defining the shapes ourselves. And what you do with this filter, you scan over the image. And at each particular place, for example here at the back of this line, you calculate the dot product, it's called. So basically you multiply one matrix with another matrix, which is kind of crop of this receptive field. And if your shape matches the shape in the image, you'll get very high score. So basically while scanning, you can get to another area, and in this case it doesn't match to the filter, so you get the low score. And as a result, of this operation, you can see here. So you take, this is your original image, and you apply these convolutions. In this case, the filter size is 3 by 3, and you generate a result. So in the result, each of these values is actually a result of this dot product of this 3 by 3 area. And then the following, apparently, if we have 64 filters here, then if we want to do it again, so we will actually multiply this number of filters dramatically. So to deal with this, what happens here is that we downsample the image twice. So the original image was 572. So by this step it becomes 568. So because the filter that was used is 3 by 3, so it actually reduces number of it reduces the size of the image by 2 pixels at each of the convolutional steps. Basically, you can see here. So because when we have this 3 by 3 filter, it can't take we can't get this block centered around this pixel because there are empty pixels here. So it starts from here. From this pixel is the first pixel of result. So the final image shrinks by 1 pixel. But when we go to this step, so what we want to do, we want to downsample our image twice. And this is done with this pooling layer. And what happens that the result of these 4 pixels could be averaged. We can take the minimum value, we can take the maximum value. There are various options, but in the standard case, we take a maximum value of all this. And as a result, instead of this 4 by 4 area, we get 2 by 2. And after that, we repeat the filters, and then we do again pooling, filters, pooling, filters, pooling, and then we get to the bottom of the net. And then after that, there's a second part of this procedure when we actually upsample the images that we have here. And during upsampling, we concatenate the filters that we have at each step with the filters that we acquired during this downsampling procedure. So this way, basically, we can combine the filters from this step with the filters that were calculated in the beginning. And at the end, we get to the final segmentation. Again, there's quite a lot of, you can read a lot of things over how it's organized, but this is very kind of short version of this. Okay, so we started the tool, and the tool is organized as this kind of workflow. So this is the first step, which is the pre-processing. Then we can do the training, and then we can go further and predict a new data set. Let's start with this pre-processing. So first we need the data. So actually, one important button here is help. So if you click on this, you'll get a detailed explanation of all these steps, what's going on. But here, the first image, which actually shows you the process. So we start with the training, and for training, we need to have a data set which is segmented. So for a data set for which we have a model. For now, for today, I decided to use this well-known example, which comes from this ISBI challenge, segmentation of neuronal structures from EM stacks. It's quite old thing and it's used in quite many different tests. And the good point from here that we can get a data set. So you need to register, and then from the downloads you can get the training volume. You can get the labels for that volume, like a model, and then we can get the volume, another volume that we can use for testing. So this dataset is coming from serial section transmission electron microscopy, and it's 4 by 4 by 50 nanometers per pixel. So I already downloaded, so have it and put it here under my project pre-processing. So I have these 3 data sets. Let's take a look on them. So let's start with the train volume. So I drag it into MIB. So this is the data set. So yeah, it's a little bit kind of shaky, not aligned, but it's quite well suited for 2D segmentation. Let's load the model. So I go to the segmentation, load. So it shows that there's nothing, but we can still open the TIFF format. And this is the train labels. So we open it as the model. So what you can see here, so the segmented part on this dataset, it's actually this space between, it's like cells, not the membranes, but rather cells. And what you see is that upon loading, it created these lots of materials. And the reason for that is that this image, this train labels, it's actually the image which has intensity between 0, which is this membrane area, and 255. And 255 is the labels, the cell bodies. So if we go back here, so we can see that, well, there is nothing in between, but there is also this material 255. So what we do, we click on this material and press Alt-A to select it. So now you can see that it's selected for all slices. Then I go to the selection menu, and then I do inversion. I invert selection. So now what you can see that our membranes that we want to predict is actually kind of there highlighted. Now I press create, make a new model, and I add a new material, and I name it membranes. And then I press Shift A to add the selection to my material. So now we have a dataset with segmented model of the membranes, and we're gonna use this for training. Since we're gonna use 2D unit, there is a certain requirements. They're all described here in the help. So for example, you can get multiple information about all the buttons and options here. And one of the important things here is, like, you can see the typical organization of the project. So like, again, my project, I have directory for training, prediction, results, and so on. We will talk about this in a moment. But what's important here is this organization. So if you use 2D network, then you need to have your images, like one file should have one single plane, and it should be supplemented with the model in one single file. And for 3D networks, we should have each 3D dataset should be a separate file, and it should have corresponding model. So in this case, we have multiple images and one model, and for 3D we have number of images should match number of models. How we do this? So first we need to save the image. So we go to File, Save Image As. Then we go create a new folder. We name it 1 Training. And there are multiple options. So we can save it as TIFF, or we can save it as a mirror mesh binary. So I typically use the mirror mesh for my stuff. For now, I'll use just TIFF. But in general, the mirror mesh is better if you have multicolor images with 2 or 4 color channels. If you have 1 color channels or 3 color channels, the TIFF is fine, because this TIFF is more like photo TIFF, so it has either 3 color channels or 1 color channel. So we have now 1 color channel, so we use this uncompressed TIFF. When we're saving and then we can actually during saving and put the pixel size. Remember that they were 004, 0.004, and 50. When we save things, there is an option to save it as 3D stack or 2D sequence. Since we're now gonna use 2D unit, we have to use 2D sequence. So we select 2D sequence and press OK. Now if we go to that folder, we can see that now we have this collection of images. And each image is like individual slice. Now we need to supplement it with the model. So I go to model, save model as, go to the same directory, 1 training, and just save it here. So I have the images and 1 single model file. How about the prediction? So we also have the prediction, which is called like the image of prediction, which is called test volume. So I'll open it as well. And I also go to File, Save Image As. And because it's the where did I have it? My project training here. So I'll make a new folder. I call it to prediction. You can call it to test or whatever you want. And I save it here also in the TIFF format. And again, I put the correct pixel size. This is optional. And then save it as 2D sequence. Okay, so this is the second folder, and I have I have here the dataset that I will use for testing. Okay, so the first step in this DeepMIB, we need to define the directories. So let's do this. So first directory is the one that has images and models that we'll use for training. So I go here and select this one training directory, select folder. The second one is the directories that we're going to use for prediction. So we click here, prediction, select folder. And the final one, the one that we use for training, for results. So we don't have it yet, so we create 3 underline results. And select this folder. Right. So now the next step, we need to define what kind of file extension we're going to have in this. So there are multiple of options. There are some standard image formats, but you can also tick this bio checkbox, and in this case you can use this bioformats reader, and that gives you the possibility to open all kinds of microscopy formats like CZI from Zeiss, or maybe lay, where is it? Here, lay or leaf from Leica. But for now we're going to use standard TIFFs, so just select TIFF in the both cases for training and prediction. And we can compress the images and the models, or we can do it like separately. Normally it's nice to compress the models because the compression factor is very good there. The next field here allows us to define the fraction of images for validation. So remember I showed you the scheme here, and what happens at this moment that if we have our images, we can actually split them for training and validation. It means that what happens during the training of the network, that the network gets trained extensively over this set of images, which has the most of the splitting part, but then it validates itself over these unseen images. That allows network to evaluate itself more precisely. Usually it's better to do the split, but of course if you don't have that much training data, then you may keep this validation fraction at 0. Then all the images which you have in this with the models will be used for training. So for now let's define here point 2. And then we have to do this preprocessing. So we can do preprocessing for training, for prediction, or for both. Since now we have both datasets, so I selected training and prediction and press this preprocess button. Okay, so the image is preprocessed, and if we go to the results folder, we can see that there are 5 directories created. So these 4 directories have images for training. So there are 24 images, and the corresponding directory train labels has 24 images with the models. And the images here are kind of randomly split from the original dataset. So you can see that this is 1, 2, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 16. So they randomly split, but they split in the same order. If I do the splitting again, the order will be the same. So the idea is that it allow a little bit like better tweaking of the procedure with different parameters. And then the validation images, that's going to be the images that we're going to use for validation. There are just 6 images in this particular case. The prediction images is the directory which is created if we select here preprocess for prediction, and it has the preprocessed these 30 images that we have in the prediction directory. Sorry, it's the different folder. So here. So these 30 images are converted to this MATLAB format, and it created 2 directories for results. Okay, so we did the first step, which was preprocessing, and then we go to the real fun, which is training. So in the training, the first thing that we need to do, we need to define what would be the input page size. So the input page size, it basically defines how big data set or an image is going to the network. So in the original UNet, the size of the image that they used was 572 by 572 pixels. So in this case, if we want to reproduce this, the real network, then we need to put here 572. That's our height, 572 width. Depth is 1, and we have one color channel. So that would be the value to make it as the original UNet. The next thing here is define the padding. So the padding is the, like, remember what happens here, that because this filter, the convolutional filter, it has this edge, so it can't calculate for this pixel because it has no information about this area. So what could be done if the padding is the same, then this original image is padded with the, I think it's a 0 value, which is kind of a bit weird, but it's just a 0 value around here. And because of that, it actually allows you to have to do this calculation without decreasing size of this window. There are certain benefits. For example, the input page size could be almost anything, but it doesn't predict things that well. So I usually prefer to use valid option, but sometimes you can't really go with valid, so you're limited to only the same padding. So for this test, we're gonna use padding valid. So we're gonna have the same way as in the classical UNet. So the images will be smaller by the size of our filter that we're gonna use. Okay, then we need next step, define number of classes. So remember that we have, let's go back to our training set. So I load the datasets and I load the model. Okay, so we have our image, and our model has one material, which is membranes. So, but in reality there are two materials. So one material is membrane and the other material is the exterior. It's everything else. So we don't have to specify it as a separate material, but here we just need to say like how many classes, in this case it called, we have. So we have two. We have one is membrane and another one is exterior. So we said put 2 here. The next step is define encoder depth. It's the how many levels these U letter will have. So 1, 2, 3, 4, 5. I think it's like this. So we can put 4. The next parameter is number of patches per image. So let's say if this is our image and the size, our input patch size matches the size of our image, so technically we should have 1 here. But the good thing is actually that what we can do, in this case we just have like 30 images, or actually less, 24. But what we can do, we can use this augmentation. Augmentation is the process when this input patch that we send to the network gets deformed with various methods. If you go on the settings button for 2D and 3D, they're kind of individual settings for each of those, we can find the different parameters. So for example, in this particular case, what we'll do, the image that will go to network could be randomly reflected, could be in X and Y, could be rotated, and these are degrees, the rotation angles. It could be scaled. Then if we do the scaling in the XY, so we can't really define separately X and Y scaling. Then could be share in X and Y direction. So we can specify all these parameters. And in this case, I would normally, it's easy, you can calculate this number of page size by the proportion of the page versus original image. So let's see, our image is info, so it's 512 by 512 pixels. So we can't use this 572. So let's put here 512, 512. So in this case, our patch is 1. Let's say if it will be 256 by 256, then it's a quarter of this image. So it means that we can technically get these patches as 4. And these patches are kind of random. So we can even have a little bit more than this, let's say 6. And then if we have augmentation, so we have, let's say, 1, 2, 3, 4, 5, 6 different augmentations, but they go as this kind of random combination, I believe. So we can actually multiply it like 6 by 6, something like this. In this particular case, let's put here, go back 512, 512, and let's put, well, I don't know, 64, 48, something like that. And the next thing that we can specify is the mini batch size. The mini batch size is the when we give the an image to network. If we want to give it one image at once, then we just put one. If we want to give, for example, 4 images at the same time, we can put like 4. We can put any number. It's just defined by the amount of memory that we have on our GPU. The more the high number here, the quicker the process will go. But we should understand that during the evaluation, the score that gets minimized during training is actually average, which is calculated from these 4 images that go to the network. So if you have some unbalanced classes, there could be some kind of limitations due to that. Next parameter is number of first filters. So in the classical UNet, they used 64. So now I have 32, but I can put 64. And the filter size is the size of this window that scans. So this is window 3 by 3. So the filter size is 3 here. So typically we use odd numbers like 3, 5, maybe 7. But the standard one is just use 3. And there's certain settings here. So we can define the input layer. And in the input layer, we can set the different normalization. So when the images go to network, they could be scaled in the different ways. So the default settings, which is 0 center, which takes an average or mean of the image and kind of moves it to 0, works quite alright. But there are a number of other options. I guess the normal way of doing this, if you see that your training doesn't really work well, what you can try to do, go to this input layer and change the normalization. And the result of this you can actually check later in this Activations Explorer that I'll explain in a moment. Then we can specify different parameters for training. For example, the solver name, this ssTEM works quite good. There's a help. You can click on this, it will get to MATLAB help system that describes all these parameters. We can specify the validation frequency if they have this validation data set. And there are a few other options here. The important part is the segmentation layer. It's the final layer of network that does the actual segmentation of things. There are 3 options here. But in biology, again, I guess this dice pixel custom classification layer is more preferable, because what you can have, like in this case, we have membranes everywhere, so it doesn't really matter. Like this will work pretty nicely. But if there is a situation when you have this other class, which would be, let's say, mitochondria, which could be like here and there, so they're quite rare. So to balance this, this dice pixel custom classification layer would work better. So probably that's why it said I put it here as default one. But you can also play around with the alternative solutions. So okay, we have, if we want augmentation, we clicked it, and when we're happy, we can check the network. So I just press here, and whoops, it says there is the error. So if you look here, there's it's self-explanatory. So what it says that the size that we put here, 512 by 512, can't be really achieved, because what happens is that when we have this complex network with this padding, there are certain limitations what kind of the size you can actually patch size you can use. But the good point is that MATLAB suggests the closest value. So in this case, it suggests to use 508, 508. So what we're gonna do here, we just go here and change this to 508, 508, because it's smaller than the size of our image. It's slightly not optimal, but it's still alright. If we would use the same padding, it actually would work right away. Then for those who use compiled version, this check oh, let's actually press this. So this check network is not really work the same way, because this window that MATLAB displays, it's not kind of, you can't really deploy it. So there will be a little bit less, not as nice representation of the network, but you'll still see this tree. And then in this particular case, if you're with MATLAB, you can actually nicely go through this layer and see various details, like for example, what size of this layer, how many filters it has, and so on and so forth. It's kind of very convenient way of evaluating the network and checking for any errors that might appear. Okay, and the last two checkboxes here before we start, we're already half an hour in the process. It's the save progress after each epoch. So what happens is that when network trains, the epoch is the when we have the 64 images, that they will go through 64 patches per image, and number of images, which is 24. So then this 64 by 24, that amount of images go through the network. That would be like one epoch. So what happens, you can actually save the configuration of the network after each epoch and return back to it if, for example, something gets crashed. And at the end, we also can export the training plots. It will show like our errors. I mean, I will keep this ticked to show you results. So we're ready. So I just go and press train button. It checks whether the images were pre-processed. We did this, so I say yes, and then creates the network. And after that, it starts the this training process by showing this big window. Let's wait for a sec. Yes, so the window is popping up. So this window has two panels. The upper one shows the accuracy. So it's the percentage of kind of how well the network kind of were able to identify the classes. But it's a little bit not that informative, because the if you have like lots of background, so it's already going to be like, let's say, at 80%. So it's not that informative. The more interesting is this loss function. It should be minimized towards 0, and that's what kind of more interesting to follow. So yeah, so we started. It's already, like you see, it started at 80 because there's plenty of background. So it's already kind of trained well. But what's interesting to see, follow this loss function. So technically, we want to minimize it as low as possible, and what it's gonna kind of fluctuate. So the process can take a while, and at each 400 iterations, there is a validation step. So the network will take these validation datasets. It's from this validation images directory where we have 6 images, and use them to evaluate independently the quality of the prediction. So it will take a while, so I don't want to wait that far. Yeah, it goes quite slow. Perhaps I should have put some little different parameters. Okay, doesn't matter. So now with the iteration 60, let me actually, what I can do now, I would like to show, let's take a look what it's actually doing with this if we train it for that long. So I can stop training by pressing this button. And actually, just one note here. So this window is different in the MATLAB and the compiled version. So this window, again, can't be deployed. So I have to write my own one, but it looks quite similar. So there is an accuracy plot, there is a loss function plot, and there's all kind of supporting information you can see. But it looks a little bit different. And then to stop that one, you probably need to click on this. There is also progress window. So you're gonna need to press this cancel button there to stop. And in this one, you can also stop it by pressing this little button here in the corner. So let's stop it now. When you do the stopping, it seems that it actually tries to do a validation, and after that it saves the network. So it actually can take a while, so kind of be patient. Let's wait a little bit. So now it's stopped. There's certain accuracy. Close this window. So let's say it crashed or we stopped it due to this kind of particular circumstances, and we want to train it again. So let's see, I just close this window and I go back again to this tool. Let's say starting from the scratch. So let's take a look what I have in this folder. So in the folder, which is actually, when I actually specify training, I need to put the actual, the network file, because I kind of forgot to tell about this. So now I open the dataset. It kind of remembers what I used the last time, but still what we want to do, what we can do, we can actually go to the options and we can load the config file. So next to the network file, there is a config file, which is basically exactly the same file, but it has slight variation. So it doesn't have the network, and because of that it's very small, but it has the information about directories that we used, that we specified. So what I can do here, I can go to the options tab, click on the load, and in the load I need to go to this my project and load this config file. So what it does, it sets up all the settings that we used, specified for our network, and also puts all the directories that were used. So, and I can just press train again, and it will continue from that point using the same network file. Let's actually do this just to show you. So I remember that we simulated now the crash, and now I just press train again. Okay, the directories are correct. Okay, and then there is the select checkpoint window appears. So what it sees now that, okay, there is one checkpoint found because we stopped it. Like normally you may have like 50 files here and 50 entries. But the first action, and we can specify any of these checkpoints, or we can select the final network that was generated. So if I click here, what it does, it takes the saved network and use it as the starting point to continue training. So let's say if you trained for like 10 epochs and you stopped, now you can actually continue this training, and this training will be started from the last point of the previous training, which kind of indicate that you can always, you have possibility to continue training with already trained network, and depending what kind of data, maybe you have more data there, so it makes sense in many situations. Okay, so the training started, and so normally it's kind of starts from this last point of the network. All right, so okay, so we did this training for, well, not as many iterations as I kind of like to, but let's take a look on the results. So for now, I'll stop the network training again, and then we will go and try to evaluate what kind of things we have there. So we're stopping it. Again, it'll take a while. I'll just pause the video here because I don't know, it's quite slow, in my case at least at the moment. Alright, so results stopped. Well, we have quite low accuracy. Loss functions also not nice, but let's see what we have. Okay, let's quickly take a look. Let's go to this predict step. So now we have a network, which is this MIB file, and we can open it. So I go to the predict tab, and for example, if I just get this network from somebody else, I just can go directly to predict tab and click here on network file name and select the network. Upon loading, it again sets up all the parameters that we used, including all this normalization, training settings, and so on and so forth. And to start prediction, the only thing I have to do just click this predict button. So it just double check whether the directories are correct, so should be fine. So it's creating store for prediction, and then after that it starts prediction. Yeah. Alright, so let's take a look what we have here. So if you go to results, so these 4 directories, they were created for training and they stay there. We can, if we finish, we can kind of delete them. We can also make them again if needed with this pre-processing option. Then score network. So the score network has these MAT files, and these MAT files are checkpoints. So they have this time code and the iteration number. So it's very easy to kind of to navigate through them. In addition, there are these 5 files that show these plots that we followed. So basically the accuracy plot, the loss plot for both validation and the training. And these files are comma separated files, so you just can load them. And the score file here is just the same, but in MATLAB format. The prediction images has the test dataset, individual slices, but now we have the scores, which is in a mirror mesh file. It's the prediction maps of each of the classes, and the model files, which is now one model file corresponds, for example, this one corresponds to slice number 12. If we want to open them efficiently, we can, in DeepMIB, we can click on this Load Images and Models button. So it loads the images and loads the models that were generated. So here results, basically you can see that it was able to kind of separate the membranes or the darker signal versus the kind of cellular bodies, but it's way far from the actual good segmentation yet. We can also load prediction scores, and here we have the multicolored image, and now we have two materials, exterior and membranes, and we have 2 color channels. If we have 4 materials, then we have 4 color channels. And if I click on this, I can see the probability of each of the pixels having one or another class. We can also evaluate segmentation. This requires that the directory here, with the prediction, should also have a model file. So if I put training there with my train volume model, actually maybe we can actually do this quickly. So I'll make another form, prediction of training, and I'll just copy my images that I use for training. We had very kind of quick training, so let's see what kind of results. So I'll go here in the prediction, I'll just change my update directory. So now we're gonna use this one. I preprocess images for prediction, and then I go to predict and then press predict. So now I'm predicting the images that I use for training, so they should be kind of way better. But the whole point here is just show this evaluation option. So if I click here, there is a number of metrics that you can use to calculate. The most useful ones is this Jaggard similarity coefficient, or it's called intersection over union. There's also a few others. The BF score you should be careful with this, it's very slow to calculate. So when we do the calculation, it tells us these different things. It shows this confusion matrix, how well the things get confused between each other, and then we can also save the results in the different formats, like MATLAB file. We can export to MATLAB. We can save it as Excel sheet with all these metrics exposed, saved there. Let's see. I can also load this. Yeah, well, the results still the same because we technically just were training for a very short time. What I can actually do, I had another, I trained it already once before, so I can actually, what I can do, I just copy this network from the other training, and here's the progress plot for the training. So it was trained for this 300 minutes. So I go to Predict tab, open my network, and load this new network. And actually we need to, again, return back to the different folder and process filter images again. Sorry, it should be diff this time. Because remember, it restores the settings, and the settings that were used for that particular training were different. I used different format. Okay, and then we go to predict and press the predict button. So there's one option here which is called overlapping tiles, and this option is only available if you use same padding. So let's keep this finished. So if we use this same padding, then this option is available, and I normally recommend to use this. And the idea here is that just press help button. Yeah. So here's the difference. So if we use same, remember that when we do the padding, we add pixels around our images, and as a result it may create this kind of artifacts when the patches are stitched together. So when this overlapping mode is used, it actually takes care of this, and then you get way smoother images at the areas when the patches are meeting each other. But again, the valid padding works way better. So let's check our images and models, and this is like longer training, and it's way better, so it was able to separate mitochondria from membranes. There are still errors, but it's kind of alright. One of the options here is the called Explorer. We can check Activations Explorer, and what it shows us, it actually shows us what happens inside the network. So here we can select the image that we want to use for checking. Let's say image 21. Here's an image of the patch that went to the network. So the size of this is 508 by 508. If you have a smaller, then the image would be kind of respectively smaller, and then we can actually go through the image by changing this values. Now our patch is just slightly smaller than the size of the image. And here shows the actual activation. So the first layer is the image that we got. So what has happened now, the image that went into the network in this particular case was scaled between 0 and 1. And the reason for that, this network that I loaded, it had actually this rescale 0,1 image normalization layer. So, and then what you can clearly see, the normalization parameters from here would actually affect how the image looks like in the network. So if something is not working, you can always go and check here. There could be some problems. And for example, you can also go somewhere deeper in the network and evaluate different filters. So if something is not working, it could be that it went to some different values in the filters, and this is just messing up the whole system. And with this, you can actually evaluate all the layers of the network up to final convolution layer. So you can see this is this prediction maps for one class and another class, which is very cool to see. And it actually kind of could be, let's actually check the prediction scores. Yeah, so these are these prediction scores, and then if this is image 21, so it's this one. So these two images should kind of rather match, if I'm not kind of mistaken. 21, no, it should be it. I don't think that they actually match, but technically they should, so I need to double check that. But this allows at least to evaluate what happens with the images. Maybe to update now. Okay. So yes, and then at the end, what you can do, you can save this config file to load or open it later. But technically, it's created automatically when you start training. All right, with this, I'll like to stop here, and then I'll do another video on the 3D training for using 3D UNet. And for now, thank you for your attention.